I know that the previous exercise was a little bit on the long side, but you also had to do a lot of preliminary work to import the data and inspect the data and so on to get the principal components analysis to work. So here we are with the next exercise, exercise 2. This one is going to be less time and also less coding, and more focused on the kind of theoretical aspects and less on kind of practical stuff of just getting visualization code to work. Now, the goal of exercise 2 here is to demonstrate something that I discussed earlier in this chapter, which is that you can implement the principal components analysis in 3 ways. One way is an eigendecomposition on the covariance matrix, and that you did in the previous exercise. A second way is on the SVD of the data covariance matrix. And then you can also implement the principal components analysis by taking the SVD of the data matrix itself without worrying about computing covariance matrices. Now, this method here, the SVD of the data matrix itself, that is actually a very easy, straightforward thing to do if you have a relatively small data set. Once you have bigger and bigger data sets, this just becomes computationally intensive and also just kind of annoying to deal with. So my favorite method is to do an eigendecomposition of the data covariance matrix. That's also the standard method in the field. Okay, so this is the goal of exercise 2 here. Reproduce the results that you found in the previous exercise using SVD on the covariance matrix and SVD on the data matrix. And here I give a couple of reminders. These are basically just about scaling factors, and it's about the relationship between the SVD of a matrix and the eigendecomposition of the matrix. Okay, so I'm now going to switch to Python and discuss my solution and also talk a bit about these scaling factors. Now, to show that the SVD on the covariance matrix gives the same results as the eigendecomposition on the covariance matrix, you do not actually need to implement all of the PCA, so all the steps of PCA, including computing the component scores and plotting and correlating and everything like that. You really only need to show that the eigenvectors and eigenvalues are the same, and the eigenvectors and the singular vectors are the same. And that's what I do here. Now, from this perspective, once you understand the relationship between SVD and eigendecomposition for a matrix times its transpose, so for a matrix X transpose X, then this is actually trivial. You don't even need to write this out because you know that the SVD and the eigendecomposition are the same when they are applied to a special kind of matrix, which is defined as a matrix times its transpose. Okay, still, it's nice to see these empirical demonstrations here. Again, as I mentioned in the previous exercise, we don't really care about these numbers per se. I'm not even going to bother interpreting them. What we care about is that the eigenvectors and the eigenvalues and the singular values match for all of these components. And the same thing here, the first eigenvector is the same thing as the first singular vector. Here you see there's a sign flip, right? But you know all about sign flips and the sign indeterminacy of eigendecomposition, but otherwise all the numerical values are the same. We would just have to flip the sign. Okay, so then slightly less trivial is the SVD on the data matrix itself. So notice that here we are not computing the SVD of a covariance matrix. We are applying SVD directly to the data matrix X. Now, here is an important note. This is one of several normalization factors that you need to worry about. And that is that variable X needs to be mean-centered. Now here I'm not explicitly mean-centering the data matrix, but that's because I don't need to here, because if I scroll up to the previous exercise, you can see that, where is it? I'm trying to find where I do it. I have already mean-centered these data over here. So if you didn't do this, if you were just using scikit-learn's PCA routine, then the data matrix would not be mean-centered, and then you would have to do that before computing the SVD on the data matrix. So now let me go back here. Okay, yeah, it's here. Okay, so we do SVD directly on the data matrix. And now one trick is, well, yeah, a tricky thing you have to keep in mind is that when we implemented PCA as an eigendecomposition on the data matrix, on the covariance matrix, we scaled the covariance matrix by n minus 1. So therefore, when we go back from the singular values to the eigenvalues, you need to square them, first of all, because the eigenvalues would be squared compared to the singular values. And then we also need to scale this by n minus 1. Okay, but then we don't need to do that for the eigenvectors or the singular vectors because those are already scaled, right? These are already unit norm vectors. So we don't need to scale these by n minus 1. All of that scaling that went into the covariance matrix goes into the singular values. Okay, so again, we don't need to rerun all of principal components analysis, every step of principal components analysis. We just need to show that the eigenvectors match the scaled singular values. So these are the squared singular values and then divided by n minus 1. And then we also see that the first eigenvector and the first singular vector are the same. Of course, this is going to continue for other vectors as well. Now, one thing you also have to keep in mind is whether you're using the left singular vectors or the right singular vectors. Now, this is unfortunately a little difficult for me to say exactly because it depends on how your data are oriented. If you would, do the matrix transpose, that's still, you would still get a principal components analysis if you did this. But here you would need to use the left singular vectors instead of the right singular vectors. Fortunately, though, you can always tell. So if you're unsure which orientation you need to apply here, you can always tell immediately by looking at the size of the output. So you know that when you do a PCA, the weights, the number of weights in the singular vectors or the eigenvectors need to correspond to the number of features in the data. So if we would, actually, I can just keep running it like this. Now you see that the first right singular vector is really, really large. So these are obviously not the same, and that's because this is the SVD of the data matrix transpose, which is mathematically valid, but it's just less easy to interpret because it's the component over time instead of over feature.